now design of hollow shaft. Learning objective of this session: design a hollow shaft on the basis of strength and on the basis of torsional rigidity by using SME code. Now again here important point, while designing the, why we are replacing the solid shaft by hollow shaft. Why hollow shafts are papered over the solid shafts, or why to design a hollow shafts if you have a solid shafts available in the market. The main important thing, look at this, give attention here. Now when shaft is subjected to bending moment, look at this. This is the shaft when subjected to bending moment. What is happening? You will find here, if you are going to locate its test distribution, because of the bending, now you are bending towards this side, upward direction. So this portion, outer fiber of the shaft, which is in tension, and inside part of the shaft, which is in compression. And you will get stress distribution in this way. These are the compressive stresses, and these are the tensile stresses. You will find again, but at the neutral axis, these compression and tensile stresses are zero. That means magnitude of compressive, magnitude of tensile stresses are zero. That means the magnitude of the stresses are maximum at the outer fiber, maybe this side or maybe this side. Try to understand. This is one aspect. Second aspect, look at this. This is also the shaft when it is subjected to twisting moment. And here, you know, the distribution of the shear stress, torsional shear stress, which is shown here because of the twisting moment or a torque. So you will find again here, this magnitude of torsional shear stress is maximum at the outer fiber or here also. Look at this other side. But here, look at this blue line here. But this is neutral axis. You will find, but intensity or these stresses are zero, or you can say very, is having very less value. The magnitude of this shear stress, which is zero at the neutral axis, even though in case when it is subjected to bending moments, again at neutral axis is zero. That means if we are going to remove the material from the, at the, you know, the central axis or neutral axis, because there is no more stresses, try to understand. Therefore, in a hollow shaft, the material is removed at the center, and because of that, what is going to happen? The solid shaft becomes more stronger than the solid shaft having the same weight. Having the same weight. Having to have a same weight, that means diameter of the shaft or dimensions of the hollow shaft is going to increase compared with the solid shaft. That is the disadvantage, but you will get the stronger hollow shaft than the solid shaft. Try to understand for the same material. So this is the logic why we are going for the hollow shaft and solid shafts converted into the hollow one, because of this stress distribution at the neutral axis. It's zero in the twisting as well as in bending. That's why. And again, you will find the maximum stresses are going to induce at the outer fiber, at the outer side. That's why we can easily convert this, you know, the solid shaft into the hollow shaft. This is the main logic behind it. Try to understand. Uh, Now let us see. That's why solid shafts are replaced by hollow shafts. And if you are going to use the same material, same length, so you will find hollow shafts are more stronger than the solid shafts for same weight. For same weight. Even for, you can find out their relation between. But while designing the hollow shaft, what you have to do? You have to check how much is the inside diameter of the hollow shaft, how much is the outside diameter of the hollow shaft. That is important parameters in design of hollow shaft. Now let us see how to design the hollow shaft. Now here some of the advantages. So you will find stiffness of the hollow shaft is more than the solid shaft with same weight. Say why same weight? Otherwise, if the weight of the hollow shaft is more or the solid shaft, we can't say like this. For the same weight, the stiffness of the hollow shaft is more for the same material also. Then strength of hollow shaft is also material for the same weight. Then natural frequency of hollow shaft is higher. than the solid shaft for the same weight. These are the advantages. Then what are the limitations? Limitation is hollow shaft is costlier. Why this costlier? So you will find diameter of the hollow shaft is more and requires more space. Again, second thing, manufacturing cost associated is also the another concern. That's why hollow shaft is costlier. Then, but what is the another advantage? Because of its, it's a hollow one. In some of the applications, it provides passage for the coolants. Again, it provides passage to control the cables in case of deep hole drilling or bore well drilling. So we can pass that coolant as well as the cables or the wires. We can accommodate inside that hollow shaft. This is also the another advantage. And you will find applications of hollow shaft in propeller shaft of automobile. You might have seen in truck or buses. You can look at the wheel, the bottom side. So you will observe it's a propeller shaft which is connected to the, by using a hook joint to the differential gearbox to the gearbox. Then axles of railway wagons, you will find hollow shaft, then epicyclic gearboxes. In epicyclic gearboxes, the other gears are runs on the other different gears shafts. That's why it's a hollow one. The hollow shafts are usually made up of extrusion process. It's a manufacturing process. This is about the hollow shaft. Let us see how to design it. Now again here in design of hollow shaft, you will find there are two criteria. Shaft design based on the strength and shaft design based on the rigidity. Strength means SYT, SUT is the criteria, depends on the material used for the shaft, and we have to find out the stresses induced in the shaft, and induced stresses should be less than the permissible stresses. You can see your design is safe. And shaft design based on rigidity. So we have to confirm the maximum deflection and maximum twisting of the shaft based on torsional rigidity. The two both the approaches remain. This approach is also same like a solid shaft. Now let us see. Now in first case, you will find when shaft subjected to torsional moment. Which shaft now? Hollow shaft. Now in a hollow shaft, I have not drawn here the diagram, but it's like a cylindrical one within, if possible. The outer diameter is DO and inside it's like a cylinder here. Suppose, if possible, I will show you the mm, hollow. 1 minute, donut here. It's okay. It's okay. It's a hollow shaft layer. I will show you here. It's okay. It's okay. Fine. Let us see. Now it's a hollow shaft. Look at this here. This diagram here. You will find it's a hollow shaft. Now hollow shaft means this is outer diameter D O, small d o suffix outer diameter, and inside diameter is the here di. So what we have to do? The here I have written small di is the inside diameter of the hollow shaft and do outside diameter of the hollow shaft. But here the ratio in some of the cases it is denoted by C. Look at this C. C is the ratio of inside diameter to outside. That means di upon do is the capital C or ratio of inside diameter to the outside diameter. Now here in this case, when this hollow shaft is subjected to torsional moment or torque, so we know very well this simple equation tau is equal to mt into r by j. R is the distance from the neutral axis. Suppose here it's the neutral axis, the outermost fiber. So what is here r? The dO by 2. dO by 2. Then what's about J? J is the polar moment of inertia of the shaft about axis of rotation. And what is the MT? Twisting moment of the torque. But here interesting one, J is going to change because it's not a solid shaft. For a solid shaft, we know that pi by 32 into d raised to 4. But it's a hollow one. That's why in this analysis of hollow shaft, only J is going to change. Therefore, polar moment of inertia of the hollow shaft about the axis of rotation. So what is the equation? J is equal to pi by 32 into dO raised to 4 minus di raised to 4. dO raised to 4 means outside diameter of the hollow shaft raised to 4. Di means inside diameter of the hollow shaft raised to 4. Again here, but we know that C, what is C? That is di by do. So you can substitute this di, replace in di is equal to C into do. C into do, but it's in 4, the C raised to 4, do raised to 4. And then again you can solve it here. So you will get J is equal to, you can take the do raised to 4 common. The J is equal to pi into do raised to 4 in bracket. It comes outside, the 1 is remaining. 1 minus C raised to 4 upon 32. This is J. And what is R? I have already told divided by 2. So you can substitute the value of J. You can substitute the value of R here. So you will get tau, that is permissible stress or torsional shear stress. So you will get this expression. The tau is equal to 16 mt upon pi do cube in bracket 1 minus C raised to 4. But what is C here? C is di upon do, or even though you can substitute here. C raised to 4 means di raised to 4 upon do raised to 4, no problem. This equation is applicable for hollow shaft when subjected to torsional moment. I hope you understood what I mean. Try to understand. This equation is applicable for hollow shaft when subjected to torsional moment. Now let us see another point when this hollow shaft is subjected to bending moment. Again here, as usual equation, I have already discussed these points yesterday also and in earlier first session also. The sigma b is equal to mby by I. This is bending stress. Mb is the bending moment. Y is the distance from the neutral axis. I is the moment of inertia of cross sectional about the shaft, about the axis of rotation. So what is happening here? Here I is going to change for the hollow shaft. Why? That is dO by 2. We know very well. When shaft is subjected to bending moment, only in this equation sigma b is equal to mby by we have already used this equation for solid shaft also. To replace this y by dO by 2 and I by, that is mass moment of inertia by this equation. For solid circular shaft, I is equal to pi by 64 into d raised to 4. But for a hollow shaft, I is equal to, for circular, I is equal to pi by 64 into do raised to 4 minus di raised to 4 bracket complete. This equation we have to substitute here. But again we know that what is C? Di by do. So you can replace di raised to 4 by C raised to 4 into do raised to 4. And then take do raised to 4 common from this bracket. So you will get pi into do raised to in bracket 1 minus C raised to 4. This. You can substitute this value and y is equal to do by 2 here. So what you will get sigma b? The sigma b is equal to 32 mb upon pi do cube in bracket 1. That means only here the change, you will get empty, here you will get the 16 compared with the torsional moment. So this is the equation for bending moment or to find out the bending stress in hollow shaft. Simple one. Now we have two equation. Two equation means first one this equation and second one is this equation where 16 MT here 32 MB. Try to understand. This is about bending moment and this is about twisting moment. After that, what you have to do? Generally, you will find, and as per our yesterday's discussion, shaft is subjected to combine twisting moment as well as the bending moment. And when it is subjected to combine axial, bending, twisting, so what is the criteria? So yesterday we have used Moore circle to find out the principal normal stress, that is sigma 1 and then tau max. But today I am not going to construct the Moore circle to get the value of sigma 1 tau max. Assuming you are very well known how to draw the Moore circle and same fundamental we are going to use it. So what you have to do when the hollow shaft subjected to combination of twisting and bending moment, then directly we are going for a two theories of failure. One is maximum shear stress theory and second one is maximum principal normal stress theory. And both theories are applicable here. But when we have to go for a maximum shear stress theory, when shaft is made of ductile material and when shaft is made up of brittle material, that time you have to go for maximum principal normal stress theory. Try to understand. Now let us see. When shaft subjected to combination of twisting and bending moment, The maximum shear stress theory is applicable for ductile material. So according to maximum shear stress theory and Mohr circle, already we know tau max is equal to under root sigma x by 2 bracket square plus tau square. But here what is sigma x is sigma b. So what you have to do? We have to substitute here sigma x means sigma b, that is 32 mb pi do cube 1 minus c in year. And what is tau? Tau is equal to 16 mt upon pi d cube in bracket 1 minus c raised to 4. Already we have discussed in an earlier slide how to find out sigma b and b. You can substitute these values here. Sigma b here and tau, this tau here. After substituting these values, you will get this equation. You can take this 16 pi d cube 1 minus c raised to 4 common. After taking out what is remaining, inside the square root here mb square plus mt square. Again here this mb square plus mt square is known as the equivalent twisting moment TE. Yesterday we have discussed. So this equation is applicable to design the hollow shaft when based on maximum shear stress theory. Try to understand. And how to get the value of tau max? This tau max you can find out by using SME code of shaft design 0.30 SYT, 0.18 SUT, whichever is minimum. If shaft is, the keyway is present, reduce it by 25%. Or you can substitute permissible shear stress for the shaft material, that is 0.5 SYT upon FOS. By using this equation, you can easily find out the diameter, that is DO. And you know the relation of this C di by DO. You can substitute here, you will get DO. Once you will get the DO inside diameter, you can find out C is equal to di by DO. So these equations we can use to design the shaft based on maximum shear stress. And similarly, we will see how to use the another theory, that is maximum principal stress theory. According to this theory, permissible value of principal stress sigma 1 is equal to sigma x by 2 plus under root sigma x by 2 bracket square plus tau square. And already, yesterday also we got this, the magnitude of sigma 1 from Mohr circle also. It's applicable or according to the maximum principal stress theory. No problem. It's okay. So what you have to do again? Sigma x is sigma b, this value. And tau means 16 mt upon pi d cube in bracket 1 minus e raised to 4. So you can substitute tau here, sigma b here, and here also sigma b. After substituting, you will get this equation. And final equation, you can solve it. Takes this 16 pi d cube in bracket 1 minus e raised to 4 common. After taking this common out, what is remaining? Mb. Here also under root mb square plus mt square. And this mb plus under root mb square plus is known as the equivalent bending moment. And this equation you can use according to this maximum principal stress theory to find out the di or do of hollow shaft. And if it SME code is not mentioned, you can put this sigma 1 or principal permissible stress SYT upon FOS. You can substitute here and solid, same like a solid shaft. This is about the design of hollow shaft. Try to understand. Fundamental same. Only what are the changes? That neutral y, mby by I is going to change. And in case of torsion, that is J, polar moment of inertia is going to change, and value of Y, distance from neutral axis, is going to change dV by 2. Other, the analysis remains same like a solid shaft. Now let us see, and this maximum principal stress theory is applicable to brittle material. Now let us see how to design the hollow shaft against this torsional rigidity. The shaft said to be rigid if does not twist much due to torque. Now look at this diagram. Same figure I have used here. Torque is subjected to twisting moment. What is happening? There may be, when it transmits the torque, there may be possibility of twisting of shaft. This angle of twist, which is denoted by theta in degree. Then G is the modulus of rigidity. And MT is the torsional moment. Again, yesterday we have already discussed what is the expression to find out the theta angle of twist. The mtj is equal to g theta r by L. L is the length, or you can say this equation. theta r is equal to mtl by jg. G is the polar moment of inertia. But again, for a hollow shaft, what is J? Pi by 30t d raised to 4 minus di raised to 4. This is J. So you can substitute only the J here. MT remains same. L length of shaft. G, that is modulus of rigidity. After substituting the value of J here, what is going to happen? You will get the theta. So this is J. Substitute here. You will get theta angle of this 5 at 4 mt into L upon G do raised to 4 in bracket 1 minus C raised to 4. And in other, for a solid shaft, what is this equation? G is equal to 5 at 4 mtl upon GD raised to 4. But what is the change for hollow shaft? G into do raised to 4 in bracket 1 minus CO raised to 4. And this is because of this polar moment of inertia for a hollow shaft. Try to understand. Otherwise, in this way, we can easily find out the theta in degree, and you have to check whether this theta is within the permissible limit or not for machine tools for line shaft. If they are within the permissible limit, you can say your design is safe. This is about the torsional rigidity. I hope analysis. Now let us see. Suppose maximum shear stress theory. You have this equation now. If somebody you have to design a shaft, hollow shaft according to SME code. So what changes you have to do? This MB should be multiplied by KB. MT should be multiplied by KT. That is the difference. And here, this tau max, you can find out from SYT, SUT multiplied by 0.30 SYT, 0.18 SUT, whichever is minimum, again reduced by 25U. This value you can substitute and you will get the dimension DO or in terms of CDI by DO. Try to understand. That is the difference. This is about SME code for shaft design. Now let us see one problem on hollow shaft. So you can take your, use your notebook and pen and try to write down this problem. It's a solved problem from V. Vandari's book, just for understanding purpose. What you have to do, you can use your notebook or a pad or a pen to write this statement. Write down. I am going to read it. Hollow transmission shaft having inside diameter zero point 0.6 times outside diameter. What does it mean? The relation between inside diameter and outside diameter is given. The C is equal to di by dy is equal to 0.6. Is made up of plain carbon steel. Plain carbon steel means 40 C8. SYT is given, SUT is not given. But factor of safety is given. And here in this statement, it is not mentioned. Use SME code. So what you have to do, tau max permissible, you can find out SYT upon factor of safety. But if you are going to say plain carbon steel means ductile material, so how to find out the permissible stress? 0.5 SYT upon FOS. The tau max permissible is, you can write tau max permissible is equal to 0.5 SYT upon FOS. You will get permissible stress. Then belt pulley 1000 mm in diameter. Pulley diameter is given. Is mounted on the shaft. The shaft के ऊपर mount है. Which overhangs? It's in hanging position. The left hand bearing by 250 mm. The left side there is one bearing and pulley is hanging, having diameter 1000. But how much is the hang distance? 250 mm. Belts are vertical. That means belt transmits power vertically to a machine shaft. So you can show T1 and T2, tight side tension, slack side tension vertically. Tension on the tight side and slack side also given 3 kilonewton, 1 kilo, 3000 Newton, 1000 Newton. While the weight of the pulley is also given. Always weight of the pulley acts vertically downward, 500 Newton. Angle of wrap of the pulley is also given. Angle of wrap means how much is the contact of the belt with the pulley, that is 180. That means half portion of the pulley there is a contact. Then calculate outside diameter and inside diameter. So you can write given data. I will give 1 minute to you, more 1 minute to write this problem statement in your notebook. You can write. It's a solved problem from V. Vandari's book. Today I will discuss an explain to you. Because of that, you will get an idea how to solve the problem. It's a solve problem. No, I hope. Now write down given data. Now here it's a diagram. Now what is given? The pulley having 1000 mm diameter, which is mounted at one end, which is overhang from the bearing, which is at its left side. Look at the figure. Bearing I have shown towards left side. Its overhang 250 mm. This pulley diameter 1000. And again here weight of the pulley is given. Again, it transmits power vertically. T1, T2, tight side tension, T2, slack side tension. The T1 is given 3 kilonewton. T2 is given 1 kilonewton, means 1000 newton. Then total load here vertically, which is acting on the pulley, because it transmits power vertically. The T1, T2 that you have to take into account, T1 plus T2. But weight of the pulley also always act vertically downward plus W. The total load you will get here, T1 plus T2 plus W. So what is the weight of the pulley? 500. So you can add 3000 Newton plus 1000 Newton plus 500. How much you will get? 4500 Newton here. Okay. Then FO is given, SYT given, DI ratio is given. DI is equal to 0.6 by dy, or dy by dy is equal to 0.6, or C is equal to 0.6. Now let us see, diameter of pulley is given. So what you have to do? So first of all, find out torque transmitted by the pulley or belt drive. So yesterday we have solved one problem. The MT is equal torque transmitted by the pulley or a belt drive. MT is equal to T1 minus T2 into pulley radius. So what is tight side tension maximum? 3000. Slack side tension 1000. What is the pulley radius? Diameter is 1000. So here 500 is the pulley radius. So you will get 3000 minus 1000 into pulley radius 500. You can solve it. You will get MT is equal to 1000 into 10 raised to 3 Newton mm. Then second, this is MT. Now from torque transmission, you will get MT torque. Then what you have to do? We have to find out the MB. Yesterday we have seen to find out the magnitude of bending moment. We have constructed vertical load diagram. We have constructed horizontal load diagram. But in this case, only this pulley transmits power vertically and weight is also acting vertically. That means only vertical diagram is sufficient. So therefore, it's a overhang. Look at the figure here. You will get here. So you can construct your reaction at the bearing here and vertical load T1 plus T2 plus W at a distance of 250. So how much is the bending moment at this point? T1 plus T2 plus W into this distance. You will get the MB directly. So we are going to write here. The MB is equal to T1 plus T2 plus W into that hanging distance, that is 250. The bending moment you will get 1125 into 10 raised to 3 Newton. This is MB. Once you know MT and MB, so we know the C, that is the ratio of inner diameter and outer, it's given 0.6. Therefore, what you have to do? Use this expression of hollow shaft. Tau max is equal to 16 upon pi dO cube. I have already told when it is subjected to combine. Maximum shear stress theory equation. Look, even though I would like to show the equation of according to maximum shear stress theory, look at this. Where is maximum shear? Look at this expression. According to maximum shear stress theory, tau max is equal to this, because I am going to use same equation in this problem. Look at this here. So you will get tau max is equal to 16 pi dO cube in bracket 1 minus c raised to 4 under root MB. But MB already calculated here 11,000, sorry, 1125 into 10 raised to 3 MT from torque 1000 into 10 raised. You can substitute these values here. Now here I have not used KB and KT because it is not mentioned use SME code of shaft design. If it is mentioned and if you would like to use, you can multiply it by your KB and KT. Try to understand. But in this problem, it is not mentioned. That's why I am not going to use it. Then what is tau max? Tau max is the torsional shear stress permissible for the shaft. How to find out it? Sorry, it's a shear stress, not torsional. It's a permissible shear stress. Permissible stress, shear stress, how to find out? SYT is given, FO is given. So 0.5 SYT upon FOS. So you will get 63.33 Newton per mm square. The tau max permissible is equal to 0.5 SYT upon FOS. So you can substitute this value, you will get 63.33. And solid, you will get DO here. And why this C is substituted? Because C is equal to 0.6. So you will get DO is equal to 51.81 mm. And once you will get a DO, so we know that C is equal to DI by DO. Therefore, DI is equal to 0.6 into this DO 51.81. So you will get DI, inner diameter of the hollow shaft, 31. That's all. This is about the hollow shaft problem. So what is the difference between solid and hollow? Only polar moment of inertia J and then I, and the distance from neutral axis to outer fiber, that is y is equal to dV by 2, are going to change. And because of that, the equations according to maximum shear stress theory and equations according to maximum principal stress theory are going to change. You can use these equations for hollow shaft. It's very simple analysis. Try to understand. This is about the problem on hollow shaft. Now let us see here another one simple problem. This is I will give the hint you. You can solve it. You have a notebook, you can write down because you have to solve at home also. Because today I will give hint only. Such a type of problems generally asked in gate examinations also, in our INSEM or final examinations also. Now I am going to read the problem statements. You please take 2 to 3 minutes to write the problem. Write down this problem. A solid shaft of diameter small d is used in power transmission. Due to modification of the existing transmission system, it is required to replace the solid shaft by hollow shaft of the same material and equally strong in torsion. Further, weight of the hollow shaft per meter length should be half of the solid shaft. Determine the outer diameter of the hollow shaft in terms of small d. You can read problem statement carefully. For that purpose, you can spend more than 2 or 3 minutes. Instead of giving hint about this problem, I will tell some, the important points. Look at this. Solid shaft is replaced by hollow one. Why hollow one? I have told you at the neutral axis stress intensity 0 or negligible. That's why hollow shaft gives more strength than the solid shaft. I have already explained that point. Second thing, while replacing it in this problem, solid, because torque transmission equally strong in torsion. That means torque transmission of hollow and solid remains same. Further, weight of the hollow shaft is half of the solid shaft. By using these two criteria, we can find out outside diameter in case of this. So what is given in this statement? Look at this. Torque transmitted by solid shaft is equal to torque transmitted by hollow. What is the equation for torque transmitted by solid shaft? Pi by 16 d cube into tau. And what is the equation for torque transmitted by hollow? This equation. You can compare this. So what you will get? Tau permissible. It is made up of same material. That means tau permissible same. You can cancel it. Pi get cancel. Only here d. Here you will get the expression in terms of d, do, di. So you will get this equation. This is equation 1. Again, what is mentioned? Weight of the hollow shaft per meter length should be half of the solid shaft. Now, like another hint I would like to give here. According to this, weight of the hollow shaft per meter length is half. So what is the weight? You know, the mass is equal to, or mass is equal to m by v is equal to density. The mass is equal to density into volume. And again, density is a material property, and volume means length into area. The weight of the hollow shaft is equal to half of the weight of the solid shaft. It is given in problem statement. The weight of the hollow shaft can density into length into area, and here half of the weight of the half into density into length into area. Again density, it is made up of same material. Density of both hollow and solid remains same. Density get cancelled. Length of both the shaft same. Hollow and solid get cancelled. What is remaining? Area of hollow shaft, and here area of solid shaft, but half of the area. That's why this is area of hollow and this is area of solid. But in the statement half this equation, you can solve, you will get another equation, and solve this equation 1 and equation 2, you will get the relation. This is small assignment to you for homework. You can